Hello everyone, I'm continuing to rewrite my DirectX engine into Vulkan, and today, crazy progress awaits us.
Last time, we left off with a window that blinks in blue color. Wow, very impressive. Anyway, it's time to get cooking. Let's do some rendering. Rendering can be done in many ways, and an interesting way to draw something in Vulkan is using compute shaders. This type of drawing is the most similar to drawing on a piece of paper using pencils, where we manually paint each pixel. Compute shaders have many applications, from doing various visual effects to rendering entire scenes defined in the shader itself, such as this shader written by Byte Mechanic that can be found on ShaderToy. With the help of my god-level Vulkan developer friends, I was able to modify the shader to run on my engine. It doesn't move because we are not actively modifying data used by the shader right now, and if we want to see something change, data needs to be modified on the CPU and then passed to the shader. A very simple and fast way to pass small amounts of data to the GPU in Vulkan is using push constants. Push constants are a small block of data that can be sent to the shader at draw time using commands recorded into the command buffer. They are very fast because they don't require descriptor sets, buffers, or memory allocations. We just push the data directly with a single command. The VK Guide tutorial does a great job explaining this, and I was able to easily send a matrix of floats to the shader. Inside this matrix, I stored the current frame as one of the variables. By using it as a time variable, we have successfully made the camera move in the shader. Compute shaders are very cool, and I will definitely come back to them in the future, but they are not the main topic today. A more difficult way to draw on the screen is using rasterization. Before I even started working on this, I implemented IMGUI into the engine, as it is very useful to see some values being constantly displayed for debugging purposes. This time, I'm using the docking branch that allows the windows to dock and float outside the application. Very nice! Anyway, unlike running compute shaders, geometry rendering is much more complicated in my opinion and requires more advanced pipeline setup. I will get you up to speed if you're not familiar with how this works. We first define an array of points in 3D space that form primitives like triangles. The vertex shader transforms these vertices into clip space, applying transformations like position, rotation, scale, and the camera through matrices. The GPU then determines which pixels on the screen are covered by these primitives, and the fragment shader computes the final color of each pixel. The high-level overview is pretty simple, but oh boy is it a pain to set up. Let's go over my progress in order. First, of course, we are going to render a single triangle. This involves setting up a new graphics pipeline. VK Guide provides some template code for this, and we have settings like input topology, cooling modes, blending, depth testing, anti-aliasing, etc. This template will be reused for most pipelines, so I only need to get familiar with it once. So, once again in my life, triangle. How to draw a triangle. In the shader, I could just hard code the vertex positions and colors and render it like so. To change the triangle's position, I would have to recompile the shader and restart the application. Not good. I need a different way to do this. Objects will be moved in the CPU code, so I want to pass this information from the CPU to the shader. Lots of objects could take megabytes, and push constants are far too small for that. Instead, we will use a different method of transporting geometry data: vertex buffers. In a simplified way, vertex buffers are buffers in the GPU accessible memory that store vertex attributes like positions, colors, and normals. When running the vertex shader, the GPU can fetch these vertex attributes from the buffer. On the CPU side, we need a mesh structure. A mesh in graphics programming describes the object's topology with vertices. It can also include colors, normals for lighting, UVs, and so much more. VK Guide also provides template code for this, and using it we can set up a basic mesh consisting of two triangles to form a square. Before rendering, we specify what vertices we want to render and how they should be indexed to form triangles. And finally, we render them using the Vulkan draw index command. Here is our rectangle. Pretty cool. Technically, creating meshes like this in code is already enough to make any model. And actually, that is what I was doing in my DirectX 11 engine. I had functions to generate meshes for cubes, spheres, and cylinders. But this time, we will do better. A very important thing for any modern rendering engine is to use models exported from other software. I don't want to hardcode all geometries inside my code. I want to export a model from modeling software and render it in my engine. To achieve this, we will use something called GL transmission format, or glTF for short. This is a modern 3D asset format designed for efficient runtime loading. You might be more familiar with FBX files. While they serve a similar purpose, glTF is more suited for rendering applications. On the CPU side, we already have a mesh object that stores vertex data, so importing a model essentially means reading this data from a file format like glTF and converting it to the same internal structure. The glTF file itself contains serialized model data. Right now we only care about the vertex positions, colors, normals, and UVs. The file can contain multiple meshes, and the example file given in the tutorial is exactly that. I was able to finally read all the meshes without crashing my application, and this is what we get. You might recognize this model and wonder, why is it upside down? This is where rendering becomes a much more complicated topic. Now, the upside-down model comes from differences in coordinate system conventions. Depending on how the projection and viewport are set up, the y-axis can be inverted compared to OpenGL, a predecessor to Vulkan. This can be fixed by flipping the vertical axis in the projection matrix. And with that fixed, we get this. I was feeling genuinely happy at this point. I felt like I had achieved in a short time what took me much longer in DirectX. The VK Guide tutorial and the help and support of my friends really sped up the process. I fixed some of the bugs and errors that accumulated up to this point. I was occasionally also testing that everything works on Linux using a virtual mouse and keyboard tool, Synergy. It allows me to control both computers with the same mouse and keyboard. Make sure to check out Synergy in the video description if you're interested. Now, it was time to set up some actual architecture to allow setting up basic scenes. First of all, I implemented a temporary version of a camera so I can move around in 3D space. In real life, a camera is defined by a few key things: its position, its orientation, and its field of view and aspect ratio. In code, we don't have a physical camera, we just represent it as data: position, rotation, and projection settings. Rendering is really just a transformation pipeline. We start in local space where the model exists, and it gets placed into world space alongside everything else in the scene. From here, the entire scene is transformed from the camera's point of view, taking into account its position and projection settings like field of view and aspect ratio. Finally, everything is mapped onto a 2D screen. This whole process is handled using three matrices: model, view, and projection, which are multiplied together to form the final model view projection matrix. Wait a minute. Something is not right. Welcome to programming at 3 AM. Looking at the footage, you can immediately tell that something is wrong, but can you tell what is happening? Well, we are rendering back faces in the front right now. A very long story short, the VK Guide tutorial uses reverse depth testing. That in itself is great, but the GLM library needs to have a specific definition named GLM force depth 0 to 1. Since I was not using the VK Guide repository in its entirety and was just copy-pasting code to my project, I didn't have it enabled. This made me question my entire pipeline, check every line of code multiple times, and at 3 AM start questioning my entire existence. But the math just wasn't mathing without this flag enabled. This was especially tricky to fix because the issue was hard to describe in text. Anyway, shoving the definition into my build system directly fixed all issues. Doesn't it look beautiful? Now we can finally start working on utilizing the renderer we wrote. My original plan was to port the enTT component system I wrote for my DirectX 11 engine. But the more I dug into it, the more I realized that I wrote a hot pile of garbage. I didn't want to spend another 3 months trying to rewrite it, so I need a properly implemented solution. I'll use what's tried and tested, the enTT library for C++. To properly understand how this library works, we would need a video on its own, but to use it is very simple. Think of it as a database called a registry. We can push different component types, and each component type is stored contiguously in memory. Each entity can have multiple components assigned. If we want to gather all entities that have specific combination of components, we issue a query that returns them. Simple. First of all, let's create some components. These will usually be some objects with data and functions. When we push components into the enTT registry, such as let's say a transform and a mesh component, we abandon direct ownership of these components. It is sort of a global managed storage system for application data. I was getting very excited because I knew that progress from here on is gonna get exponentially faster. So let's get cooking again. Let's rewrite a renderer to use the enTT querying. We create a transform component and a mesh component and assign them to an entity. Run this in a basic loop, and we should have 9 monkeys visible. And we should have 9 monkeys again. And here we have 9 monkeys. Yes. 100 monkeys? What is the limit? 10,000 monkeys? 30 frames per second. Pretty good. Or is it? You see, I'm not trying to build a thing that renders 10,000 objects, I want millions. While rendering 10,000 models might seem impressive, even for my now pretty old 3080 graphics card, this is essentially nothing. So why is the frame rate so low? The CPU is at fault. So we need to buy a bet. Right now, our code is submitting 10,000 rendering commands, setting vertex and index buffers, and other resources, 10,000 times each frame. Bad. We need to fix. But how? Send resources once. Good.
We want to be as monkey as possible here. Everything we can do simple, we should do simple.
How to only send resources once? With batch rendering, Vulkan provides excellent batch rendering capabilities, and the way it works is very simple. We collect the data of all geometry instances into an array, and pass this data to a slightly modified shader. The GPU renders them in parallel. I managed to finally get this running, and here we are rendering 10,000 monkeys at 144 frames per second, which is my monitor refresh rate. Let's go higher. 100,000? Here we go, 100,000 at 30 frames per second. Not bad, but we can do better. I realized at this point how annoying it is to look at my tiny window, so I implemented a proper full screen. Sorry it took so long, and you're welcome. Can we still improve our frame rate? Right now, we are not even applying rotation and scale, and if we did that, we would have a solid 12 frames per second. It's time to get serious. Without good profiling tools, which I'm not using right now, we can still make some guesses to improve the performance. First, simplify the model. This gives some improvement, but I couldn't shake off this bad feeling that I'm forgetting something. And I was forgetting something. My application was built in debugging mode, which meant that Vulkan was using validation layers, which meant that after building the application for the first time in release mode, I was happy to see that we have our FPS at 80 while rendering 100,000 spheres. Time for the final boss, 1 million entities. 8 FPS. Not good. Not good. Let's use a simpler model like a cube. This gave a drastic performance improvement of basically 3 times. We are now rendering 1 million cubes at around 24 frames per second, which in some standard is already very impressive. Having such a large array of entities feels weird. It is hard to fathom how many individual things exist on the screen at one time. They create all sorts of patterns when moving. It is really an odd experience. To get any more performance increases, I will need to start to do some sort of profiling to understand what is going on. This is a good time to understand how we manage the data for batch rendering. The entire batch rendering process happens in 3 steps: building, uploading, and recording. Building means gathering all the entities from the enTT registry and building the model view projection matrix we talked about earlier. We take the position, rotation, and scale data and get relevant matrices using the GLM library. Then we store this data for each instance in memory, contiguously. This is our instance buffer. In the shader, these GLM matrices are later multiplied with the view projection matrix to get the final render output. The uploading step is very simple. We just copy this data into GPU uniform buffer located in video random access memory, the VRAM. After this step, all of our data is already in the GPU. Recording is the last step. This is just submitting a Vulkan draw index command. The pipeline and shaders are modified specifically for batch rendering, so the GPU is able to index all of this data one by one in parallel to achieve extreme rendering speeds. Great, so where is the bottleneck? If we check how much time each of these steps takes, we can see that the vast majority of work is building the model matrices. Unfortunately, this step cannot be avoided. We must do it to get an accurate view. The good news is that we don't need to do this on the CPU side. Instead of calculating this data from transform components on the CPU, I instead can pass transform component data directly to the GPU and calculate the model matrix locally in the shader. I got a clanker to write me some functions for GLSL, and this was by far the most significant improvement made so far. After this, I did one last improvement I could think of, which is to multi-thread the building part. I essentially split the job among 16 threads using C++ threads library. Even with improper setup, which I will have fixed later, I managed to get around 80 frames per second. At this point, I was reaching the limits of my patience. Debugging and understanding bottlenecks was getting very hard. There are tons of improvements likely left to do here, and I felt that for this video, I have already done and achieved so much. At the time, I am already working on a particle simulation, and I am still finding ways to make rendering faster. So this will be an ongoing process for the engine, And I must make it clear, I am very, very happy with how this is going. The amount of progress we have made has been insane.
You know what else is insane? The amount of support I have received from you guys last video. It has been amazing for me as a content creator, and I want to say thank you.
I hope you found this interesting and even learned something new. I have a special surprise cooking for next time. Until then, see ya.